Welcome back. We're going to talk about absolute extrema on a closed bounded region. This is really, you can call this part two for problem set 9, I think we're on. So it's not part two for relative extrema, it was part two for this problem set. Well, first of all, we need to talk about what a closed bounded region is. If we have, for instance, x is between 0 and 1, y is between 0 and 1, not equaling 0 or 1, we have this square, and I put a dotted line here to indicate that this boundary of the region is not included. That's open. In 2 dimensions, a set is open if it doesn't include the boundary. And it's bounded. A very simple way to define this topological definition is if we can draw a circle around it, it's bounded, quite simply. Now in this case, x between 0 and 1, y is between 0 and 1 equals, that's this square, but it includes the boundary. It includes the boundary, so it's closed. It's bounded because we can draw a circle around it. So we're going to be looking for absolute maximums and minimums on regions like this. It could be rectangle, it could be circle, it could be triangular, whatever. So in this case, x greater than or equal to 0 and y is between 0 and 1. Between 0 and 1 is here. Greater than 0 means we can go to the right as far as we want. That's closed. The boundary is this line, and this line. It's only bounded on 3 sides. You can't go out to infinity and put a line there. Although when I was in 3rd grade, I did ask my brother what the largest number was, and he wrote down a large number and told me, and I believed it. So, but that's not true. So there is no largest number on the x-axis. This is closed but unbounded. You cannot draw a circle around this region. Okay, so it's unbounded. You can find some functions will have absolute extrema on unbounded regions. It's just not what we're talking about right now. So if f of xy is continuous on a closed bounded region, absolute extrema, max or min, occur at one of 2 places. Critical points on the interior. We know how to find critical points. Okay, we find partial derivatives and set them equal to 0. Or at the boundary. It's either its critical point of the interior or somewhere on the boundary. We're going to go through an example of how to use this to find an absolute maximum and minimum. It's fairly simple, although at times it can be tedious. And here is an example. Let's take our old friend, an elliptic paraboloid. And we want to find the absolute max and min on this. This is what's called a Cartesian product, probably named after Rene Descartes. He was the father of analytic geometry, and he developed this notation. This is the same as saying x between 0 and 3 and y is between 0 and 3. So it's basically a square. You can make this a 3 and that a 3. That's basically what this is. Well, first of all, we're going to find critical points on interior. So we're going to find the x partial, which is 2x, set it equal to 0. We get x equals 0. Fy, 2y minus 4 equals 0. Y equals 2. And so we have a critical point 0 to f of 0, 2. And what we're going to do is this. We need to clear some space. And we're going to make ourselves a chart. X, Y, f of x, y. And so far we have a 0 and a 2 for x and y. That's on this interior, by the way. And let's draw ourselves a picture of this I'll call this a Descartesian product. I think Descartes gets shorted. Everyone takes the day off of his name. So we'll call this a Descartesian product. This square. 0, 2 is actually, it's not in the interior, it's in the boundary, but I'll put it there just for safekeeping. It's in the region, so 0, 2 is in the boundary. Now, if you put 0, 2 in, you can plug into the function, that's 0. 4 minus 8, that's negative 4. At this point, could be a max, could be a min. We don't have a clue. So next, we're going to look at the boundaries, or the boundary. And we're just going to go line segment by line segment, right around this square. Let's start with this line segment right here. Y equals 0, and x is between 0 and 3. Well, if y is equal to 0, we can simplify this function. F of x, 0, is equal to x squared plus 0 squared minus 4 times 0 is just x squared. And keep in mind we're on this line segment right here. Now what I'm going to do is, this is really a max min on a closed interval. We're going to find the maximum and minimum on this closed interval. That's a Calc 1 topic. We're going to find the x partial. We get 2x, set it equal to 0, x equals 0. And that's actually an endpoint. We have 0, 0. And if we didn't have that, we would include this endpoint. So, but it's already here. And then we're going to include this endpoint right here, 3, 0. If you plug in 0, 0, you get 0 for f. If you plug in 3, 0, you get 9. That's the first part of the boundary. And now let's do this part. We're going to go upward. And right there we have x equals 3. And y goes from 0 to 3. If x equals 3, you can plug this in. We get f of 3 y is equal to 9 plus y squared minus 4y. And you're going to take f sub y of 3y is equal to 2y minus 4 equals 0. Y equals 2. And so we have the point 2, 3. That's only part way up. That's right about here. And so we have the point 3, 2. And then we want to include these endpoints. This one's already included, but this endpoint right here is 3, 3. So we'll include that. And 3, 2, let's see, 9 minus 4, 9 plus 4, we're working with 3, 2. 9 plus 4 is 13 minus 8, that's 5. And 3, 3 gives us 9 and 9 is 18, minus 12 is 6. Okay, continuing up here. We have y equals 3, and x is between 0 and 3. since y equals 3, we get f of x3 is x squared plus 9 minus 12. 9 minus 12 is minus 3. Fx, x3 is 2x, set it equal to 0. X equals 0. Well, x equals 0, y equals 3 is right here. So that's the one endpoint. That endpoint's already included from the previous step. That's that. 3, 3. 0, 3 is that endpoint. No critical points on the interior of that line segment. 0, 3, that's 0. That's 9 minus 12. That's negative 3. And now we're coming down the home stretch. Down here, we're at x equals 0. Y goes from 0 to 3. And so plug in x equals 0, you have f of 0y is equal to y squared minus 4y, fy 0y, 2y minus 4, set it equal to 0. Y equals 2. It's right here. And so we have 0, 2. And actually, these two boundary points here were included. That's 0, 3 is right here, and 0, 0 is included right here. No need to be redundant. So substitute 0 squared plus 4 minus 8. Plug in 2, that's 4, that's 8. 4 minus 8 is negative 4. And that completes our list of candidates. Where's the maximum? Right here. Where's the minimum? Actually, 0, 2, 0, 2, that was included as a critical point up here. So, so that's actually already included. So we have absolute max is negative 9. Or positive 9, sorry about that. Absolute min is negative 4. Okay. And my rescue kitty Sunshine wants to make a guest appearance. Here, say hello. We found her. She was about this big in a ditch. I don't know if she's appeared in the video yet, but she likes a little attention. Okay. That's all for this video.